In the last class we looked at two methods for the solution of Ax equal to b type of set of simultaneous linear algebraic equations. One of these was the Gaussian elimination method and the other was the LU decomposition method. In both cases we are reducing the set of equations described by Ax equal to b into a specific form, into an upper diagonal matrix form. The A is converted into an upper diagonal matrix form. In the process we are rearranging the equations, reformulating the equations in such a way that solution by successive substitution is possible. In the case of Gaussian elimination method, we are converting Ax equal to b into, we are converting Ax equal to b into a special form which is being written as an upper triangular matrix U times x here equal to a modified form of the coefficients, and this upper triangular form is such that while the last equation here contains the last equation here is a n1 x1 plus a n2 x2 plus a n3 x3 plus a nn n minus 1 x n minus 1 plus a n x n equal to b n. So this is rewritten in this modified form. The last equation is written as a n n prime x n equal to b n prime. Okay, and the one which is just above this equation here is written as a n n minus 1 prime x n minus 1. So this is a n minus 1 plus a n minus 1 n prime x n equal to b n minus 1 prime. So in this transformed rearranged set of equations, the last equation is simplified from one which involves all the variables all the way from x1, x2, x3 up to xn into an equation involving only xn as a variable. So from this we can directly get xn as b prime n by a prime nn. And once you have xn here, you can substitute this value in this and you have this equation which contains only xn minus 1. So we can, by substituting this value in this, we can get xn minus 1. Similarly, the third equation from bottom here is put in some form of xn minus 2 plus a double prime xn minus 1 plus a triple prime xn equal to b prime n minus 2. Okay, so the right hand side of this equation gets changed and the coefficients also gets changed. Okay, but by this time we already know xn and we already know xn minus 1. So we can substitute here for this and we can substitute here for this, and we have a simple equation for xn minus 2 we can get from this xn minus 2. Okay, so by successive back substitution starting from the bottom most equation, the last equation, all the way up to this, we can evaluate xn, xn minus 1, xn minus 1, xn minus 2 all the way to x1 through substitution alone, which is very fast. So it won't take a large number of multiplications and divisions. For example, here we have one division and here we have this times this one multiplication and then again subtraction of this from this and then division by this. So you have one multiplication here and one division here. So and here we have one multiplication. subtraction and division here. So as we go more and more, we get more and more number of mathematical operations, but it is only every time a few more. So the back substitution process is an easy way of solving the equations successively, but to go from a general matrix into an upper triangular matrix here requires a lot of work, and we said that that will be taking n cube by 3 number of mathematical operations, whereas the back substitution will take n square number of operations, and together it will take n cube plus n square number of mathematical arithmetic operations, which will tend towards n cube by 3 number of multiplications and divisions for the solution using Gaussian elimination method, and which is much better than the factorial n plus 1 which is required for the Cramer's rule. The other method that we looked at, which is the LU decomposition method, is similar to this in principle. In this case, in the case of Gaussian elimination, as we transform Ax equal to b into Ux equal to b prime here, the right hand side is also getting transformed. In the case of LU decomposition, we only convert A into a product of lower and upper triangular matrix, so that an equation of Ax equal to b is written as Lux equal to b, in which we know we have certain algorithms to find the elements Lij and Uij of this lower and upper triangular matrices. So when you have an equation like this, then you can put this, you can solve this equation first. So that is, you can solve, you can put Ux equal to y, okay, so that we write this as Ly equal to b. So in this, L is known and b is known, so we can get y, and this lower triangular matrix will be like this matrix, it will be like here. So we get y by starting with the first equation and second equation, third equation, like this. So this we get by forward substitution. And once we get y here, we can solve for Ux equal to y, in which case y is known and u is known. From this we get x by backward substitution. Okay, so let's just try to write it down neatly here. We have Ax equal to b converted to Ux equal to b prime and solved by back substitution. The first method is the Gaussian elimination method. The second method, Ax equal to b, written as Lux equal to b, the same b, and solving this in 2 steps as Ly equal to b, giving y by forward substitution, and this is followed by solution of Ux equal to y and solving this for x by backward substitution. Okay, so this is the essence of the LU decomposition method, and this is what we are doing in Gaussian elimination method. Both of them are good methods in the for the general case of Ax equal to b. Okay, but today we are going to look at a specialized method which builds on the same principles, that if it is possible to convert Ax equal to b into a special form, into an upper triangular form or Lux equal to b form like this, then we can get easy solution through successive substitution here. The same principle can be applied to a simple case of a tridiagonal matrix. In a case where we have Tx equal to S, where T is tridiagonal matrix. Okay. So, let us see for example, a simple case of d by dx of k dt by dx. Let me not confuse this t with this t. So, let me put this as theta equal to q. So, this is one dimensional steady state heat conduction equation where k is the thermal conductivity, theta is the temperature, and q is some heat source or heat sink in the appropriate form, for example volumetric or area wise and all that. So, we have this equation, and we have, this is a one dimensional problem. We have x going in this direction, and we can have I here, I minus 1 and I plus 1, I plus 2, I minus 2 like this. The boundary conditions at x equal to 0 and x equal to L are specified. At this point, we can discretize this by writing this as, we will put this as I minus half and this as I plus half, that is midway between the 2 points. So, we can write this as k d theta by dx at I plus half minus k d theta by dx at I minus half divided by delta x is equal to qi, and we can write d theta by dx at I plus half here as k at I plus half, and this as theta I plus 1 minus theta I by delta x minus k at I minus half theta I minus theta I minus 1 by delta x is equal to, we take this here and we have qi times delta x. Okay. So, here we see that we have theta I plus 1 and theta I minus 1. So, we can write this as k I plus half by delta x theta I plus 1 minus k I plus half by delta x plus k I minus half by delta x times theta I plus k I minus half by delta x times theta I minus 1 equal to qi times delta x. So, we have theta I in terms of theta I plus 1 and theta I minus 1. So, if you do this for every theta and put them in the lexicographic ordering, we will get a matrix A which will have all theta I values will be along the central diagonal here, and theta I minus 1 will be just here, and theta I plus 1 will be here. All these are zeros. So, this A resulting from the discretization of one dimensional heat conduction equation is a typical example where we have T as a tridiagonal matrix. So, this is the tridiagonal matrix form of the coefficient matrix T, which arises from this one dimensional Poisson equation or Laplace equation like this. So, what we would like to do is that we would like to solve this, and we would like to solve this taking advantage of this type of conversion, that is conversion into an upper triangular matrix or LU kind of thing here. So, it is possible to develop a very fast scheme by taking advantage of the fact that in this there are only 3 rows, 3 diagonals here which are non-zero and all the others are 0, and taking advantage of the fact that in a typical diffusion problem the diagonal dominance of this triangular matrix is satisfied. Okay. So, with these kind of conditions, what we would like to do is to convert Tx equal to S into an upper triangular matrix of the form Ux equal to S prime, okay, and in such a way that this upper triangular matrix will only have 2 rows. So, what we are looking at is that where you have T is such that the T I comma I is AI and T I comma I plus 1 is BI and T I comma I minus 1 is CI, okay, where A, B, C are the coefficients, so that for the ith equation in this, so you have first equation, second equation, third equation, all the way up to n number of equations. The ith equation can be written as C I x I minus 1 plus A I x I plus B I x I plus 1 equal to S I. So, the ith equation in this system is written as a coefficient corresponding to I minus 1, a coefficient AI corresponding to ith term, and a coefficient BI corresponding to the I plus 1th variable equal to SI. And this formulation is such that each of these coefficients can change from equation to equation. You can have some special cases where all the C's are constant and all the A's are constant. For example, in the simplest case where K is constant, the thermal conductivity is constant, we normally have C equal to 1, A equal to minus 2 and B equal to 1. Okay. So, this represents a tridiagonal an equation, a linear algebraic equation involving 3 adjacent neighbors, and when you go for all values of phi you get this type of form. So, this is a equation that we wish to solve for n number of xn, x1, x2, x3 all the way up to xn, and we would like to convert this into ux equal to s, where uii is taken to be 1 and I plus 1 is given as di and s prime I is given as yi. Okay. So, the form of T is this central diagonal has coefficient ai. The one corresponding to I plus 1 is the one which is above here, all the coefficients here are bi, and the one I minus 1 is 1 below and this is Ci. Okay, so, these are the coefficient values, and these values may change in each equation as we mentioned here. This is being converted into a special form of upper triangular matrix where we have all the diagonals have 1 and we have only one more diagonal here, and this is yi and all these are 0. Okay. So, if you can make this conversion here, then this equation can be solved in the back substitution process. Okay, we have this one directly giving us xn, and this one will involve xn and xn minus 1. We know xn, so we can get xn minus 1. We go to the next equation. The next equation involves only xn minus 1 and xn minus 2. We solve for xn minus 2. Then we come here. This will involve xn minus 2 and xn minus 3, and so we know xn minus 2, so we can solve this for xn minus 3, and we can just climb the ladder, as it were. You solve this, and then you go here and then get this, and then you go here, get this, you go here, get this, like this, and you can go all the way up to the first one. So this is the idea of the tridiagonal matrix algorithm, in which a tridiagonal original matrix T is converted into an upper triangular matrix containing only 2 non-zero diagonals. Okay. So how can we do this conversion is the thing that we would like to have here. So when we write an equation like this, this equation is such that the ith equation is written as xi plus di xi plus 1 equal to yi. Okay, so because uii is equal to 1, so in the ith equation you have xi and xi plus 1. Okay, xi plus 1 will be the coming here. So this is the ith equation in ux equal to y. Okay, ux equal to s prime, and this is the ith equation in tx equal to s. So whereas here you have 3 coefficients ci, ai, bi here, in this equation this coefficient is 1 by choice, and this coefficient di and yi are to be determined yet. Okay, so if this is the yth equation, I minus 1th equation is given by xi minus 1 plus di minus 1 xi equal to y I minus 1. Okay. So now what we would like to do is to convert this equation, in which we already know Ci, Ai, Bi, Si, because that is what we have derived here. So all the coefficients in this T are known. We want to convert this into this form and determine this di and yi for each of these equations, because once we do this, then it is possible to do this back substitution here. So we make use of this expression here in this. So we can write this as, so we can say from here this xi minus 1 is yi minus 1 minus di minus 1 xi here. We substitute this here and then get rid of this xi minus 1, so that we have an equation involving xi and xi plus 1, and that equation is similar to this form. This is also an equation involving xi and xi plus 1. So we compare the coefficients, and then from that we will be able to get an expression for di and yi. So what we are doing is that if this is the form of the ith equation, we are saying that the form of the ith I minus 1th equation is xi minus 1 plus di minus 1 times xi equal to y I minus 1. So this equation allows us to write xi minus 1 equal to this minus this. We substitute this value here in this, and we can write that as Ci times yi minus 1 minus di minus 1 xi plus ai xi plus bi xi plus 1 equal to si. So we can now take this Ci minus this one here, and we have ai minus Ci di minus 1 times xi plus bi xi plus 1 equal to si minus Ci y minus 1. Okay. So, we can divide this whole thing by this and write this as xi plus bi by ai minus Ci di minus 1 times xi plus 1 equal to Si minus Ci yi minus 1 divided by ai minus Ci di minus 1. Okay, so I would like you to examine this equation and this equation here. In both cases, this coefficient is 1 and this coefficient must be equal to this coefficient. So, from this we can say that this term and this is equal to this, and we have yi is given by this. Okay, so let us now write the formula here. Di is bi by Ci ai minus Ci di minus 1, and yi is Si minus Ci yi minus 1 divided by ai minus Okay, so that means that we already know ai, bi, ci everywhere and si. We do not know di minus 1 and si minus 1, but we can say that for the d1 is b1 by a1, okay, and y1 is s1 by a1. So, starting with these expressions from I equal to next point onwards, that is we can take I equal to 2 onwards, we can put d2 equal to b2 which we know, a2 which we know, minus c2 times di minus 1 by d1, and d1 is already known. So, we can evaluate d2. Similarly, y2 will be equal to s2 which we know, ci times y1 which is given here, and a1 is known, a2 is known, c2 is known, and d1 is known. So, we can evaluate y2. So, we can evaluate d2 y2, and then we go back here and we evaluate d3 y3 and d4 y4 all the way up to dn by n. So, using this recursive formulas, starting with known values of d1 and y1 from the form of these equations, we will be able to get determine all the coefficients of di and yn. Then it is a question of back substitution. So, we will write down the whole algorithm for the solution of Tx equal to S using this tridiagonal matrix algorithm, in which we write Tx equal to S in the form of an upper diagonal matrix, bidiagonal matrix involving only 2 diagonals, in which we put u equal to 1 here, all these diagonal elements to be 1. Okay. Why we want to put these to be 1? These can be any values, but these have to be fixed in order to get unique set of values here. So, in this algorithm we put all of them to be 1, and then we have exactly as many number of equations as are needed to determine this di and ya, and this can be put in this simple recursive forms. So, we from known values of ai, bi, ci, si, we start with the initial values, and then we find all the dn and yn, and through the back substitution process we get the final solution. So we will just rub it. Okay, I am continuing. The tridiagonal matrix algorithm known as TDMA, it is also known as the Thomas algorithm, for the solution of Tx equal to S, where Tii is Ai, Ti I plus 1 is Bi, Ti I minus 1 is Ci, and Si is Si. Okay. So, with this starts with conversion of this this equation, that is Ci xi minus 1 plus Ai xi plus Bi xi plus 1 equal to Si. So, this is rewritten as xi plus di xi plus 1 equal to yi, where d1 is b1 by a1 and y1 is s1 by a1, and we have di is given by bi minus bi divided by ai minus ci times di minus 1, and yi is si minus ci yi minus 1 divided by ai minus ci di minus 1. So, we start with this and then we evaluate all this from I equal to 2 to n, and once you have this, you can then back substitute by saying xn is yn by dn is the thing, and then we can write xn minus 1 is equal to yn minus 1, okay, yn minus 1 divided minus xn divided by dn minus 1, and so on. We can go through this. We can go through this until we go from xn to x1, all the way to x1. So, this is the Thomas algorithm, where we convert the Tx equal to S into Ux equal to S prime, in where U is a upper bidiagonal matrix, and then we evaluate the elements here and then we do back substitution to get this. So, the overall number of mathematical operations required for the solution for large n is about 12n, where n is the number of equations. Okay. So, this is very small compared to the n cubed by 3 which is required for Gaussian elimination and LU method, and n plus 1 factorial for Cramer's rule. So, but the advantage is that the disadvantage is this can be applied only for tridiagonal matrix. It can be applied only for 1D problems. We will see later on in the next class some other methods, and we will come back to this method in the advanced methods which try to make use of the efficiency of the Thomas algorithm in solving one particular form of Ax equal to b. Thank you.